Hi, welcome back guys. Today's lesson we're going to look at something called dynamic equilibrium in reversible reactions. So we're staying with reversible reactions. We're going to start to delve a little bit deeper into them and some of the complications and some of the things that arise from reversible reactions. And in particular today we're going to define what dynamic equilibrium is. We're going to look at what closed and open systems are. We're going to have a look at something called Le Chatelier's principle, which is named after a scientist. And we're going to have a look at what that principle tells us about the effects of change in temperature and indeed other things in a reversible reaction. So it's really important for science, and we'll look at why that is as we go along. So firstly, to understand what we mean by dynamic equilibrium, we first need to know what an open and closed system are. And a simple way of describing it is a closed system is nothing can escape or enter the system, and you can think there about a test tube with a bung in it. So nothing can escape from the test tube, nothing can get into it because the bung is stopping anything doing that. An open system is obviously the opposite, and that is where things can escape or enter, and here you can think about a test tube with no bung in it. So therefore things can escape from there either via evaporation or indeed anything else. Here's another little diagram. So here we have our closed system. So we can see energy can come in or out, so we can lose temperature through our closed system, but we can't change matter. So gases, liquids, solids can't get in or indeed out. In an open system, everything can get in and out. Okay, so difference between a closed system and an open system. Nothing can get in or out of a closed system. Things can freely move in and out of an open system. Here we have again another example. So we've got, like in last lesson, we've got our copper sulfate. We're going to heat it up to produce our water, and in this time we've got a closed system. We've got a bung in place. So as the water evaporates, it recondenses up in the colder part of the test tube and falls back down, and we end up with what's called an equilibrium. We end up with some white copper sulfate, we end up with some blue copper sulfate. In the open system, when we heat up the copper sulfate, the gases can evaporate and then leave the top of the test tube, so we're left only with our white copper sulfate as a product. So dynamic equilibrium, what is it then? Bearing in mind what a closed and open system is. If a reversible reaction is taking place inside a closed system, so where nothing can escape or enter in terms of the chemicals, the state of a dynamic equilibrium is eventually reached. Okay, so this means the amount of product and reactant reach a balance and stop changing. Okay, so the amount of product and the amount of reactant stop changing. We still have some reactants, we still have some of what we start with, and we still have something that we've made. Okay, we've got both of those, we've got both of the things on both sides of the arrows, but eventually the amounts of those stays constant. That's equilibrium. However, it doesn't mean the reactions have stopped. In fact, the reactions are still carrying on. You've still got the forward reaction from the reactants making the products going on, and we've still got the backwards reaction, the products going into the reactants. That is happening, but they're happening at exactly the same rate at the same time, so it means there's no overall change. It's a little bit tricky to get your head round at first, so just have a little think about it. You can rewatch this video again to try and understand that. Okay, and we call that dynamic equilibrium because the reaction is happening, it's constantly happening. Here's a little example. So we've got our copper sulfate in the bottom of our test tube. We've put our bung inside it, and at the start we only have that copper sulfate in our boiling tube. When we start to heat it, and we're heating it here, some of the copper sulfate changes, and water is produced. So here we can see some of our blue copper sulfate is turned into our white copper sulfate, our anhydrous, and we've got some water being produced, okay? And that will float up the side. So what happens at first is the amount of the blue copper sulfate is going down because it's being converted into the white copper sulfate, and the amount of our products, which is the white copper sulfate and the water, is going to go up in this test tube. Because obviously at the start, if we go back to the first one, we only have the blue copper sulfate and nothing else. We've just got our reactant. Now we've got our reactant and we've got some products. As we continue this reaction, we start to get more and more of the products and less of the reactants. But after a short amount of time, we end up where the amount of copper sulfate that's blue and the amount that's white stays constant, it stays the same. So we have the same amounts, and this is our equilibrium. And this is because as fast as we are turning the blue copper sulfate into the white copper sulfate by heating it, the water is condensing, falling back down again and making the reaction go in the reverse way to turn some of the white copper sulfate back into the blue. So it's a constant loop. It's almost like a tug of war, and they've reached a position where neither of them can pull the other side. They're both trying, they're both moving like a couple of centimeters one way, a couple of centimeters the other, but overall the amounts are going to stay the same. Okay, so blue copper sulfate turn into the white copper sulfate. At the same time, the reverse is happening. No change in overall amounts. Okay, I hope that makes sense to everyone. Another way of thinking about it is you can think of it like the shops at the moment. So if you go to Tesco or you go to Sainsbury's or Waitrose or wherever you do your shopping, you've got people leaving and entering the shop at the same rate. So the numbers inside don't change. You've got somebody at the front who counts the people going in and out, and when someone goes out, they let somebody else in. When someone goes in, someone else has to come out first. So the numbers inside stay the same. It's at dynamic equilibrium. There's still people leaving, there's still people entering, but it's being managed to keep the numbers inside the same. So that's a dynamic equilibrium at the shops in terms of the people. So you can tell your parents about that when they're next off to the shops. Now, need to look at the Chatelier's principle. And the Chatelier, famous scientist, French obviously from his name. Nice picture of him up at the top. His principle is very important for chemistry. And he said if you change the conditions of a reversible reaction at equilibrium, so when a reaction's already reached equilibrium, if you change the conditions, then the system will move to reduce that change or to oppose that change. So that's his principle, and you do need to know that, and we're going to break it down and explain what it means. Really, really useful, because it can be used to predict the effects of changes to a chemical reaction. So a reversible reaction. So if we've got a reversible reaction, we can say what happens if we change X, Y, and Z about it, what's the effect going to be? And that's particularly important for manipulating yields in a reversible reaction, because obviously if you've got a reversible reaction, you make your product, but at the same time some of your product is spontaneously going to break down to make some of your reactant. So we need to figure out a way to stop this happening so we can maximize our yields. Higher yield, greater profit. And yield, if you don't know, is how much of something you make. What does the word condition mean? What does he mean by conditions? Well, the conditions here are temperature, pressure, and the concentration, or amounts of things. So we're looking at inside the reaction in a closed system where nothing can escape or nothing can leave. If you change the pressure, if we change the pressure externally, either by putting it in a fridge or putting it in an oven, for example, the reaction, there will be a change in the system. The chemical reaction will change slightly to try and reduce the change that we've done to it. Same if we increase the pressure, if we're looking at reactions with gases, and also if we change the concentration of things, if we're looking at reactions with liquids. So basically, if we change the conditions, then the equilibrium position gets disrupted and we end up with a new equilibrium amount of products and reactants. So you might have had at first in your reaction 50% of your reactants on the left, 50% of your products on the right. If you change something in the equilibrium, like change the pressure, change the concentration, change the temperature, then you might end up with, say, 25% of your reactants, 75% of your products. And this is because the reaction is trying to oppose those changes. Okay, you can imagine they're quite stubborn. Okay, they are a bit like your stereotypical stubborn teenager. You tell it to do something, or you try and get it to do something, it does the opposite. So, example, you're looking at temperature. Reversible reactions, as we've already discussed in the last lesson, are exothermic in one direction and then endothermic in the other. Now, if we raise the temperature of a reaction, so for example we heat it, we put it in an oven, we stick a Bunsen burner up at the front. it will make the rate of the endothermic reaction go faster so more of that product is made. So it will go in the endothermic direction because it's trying to resist the changes that we're making by cooling itself down. Conversely, if we reduce the temperature, for example we stick our reaction inside a fridge, it'll make the rate of the exothermic reaction go faster so more of that product is made. So it's trying to oppose the cooling, it's trying to give out heat to oppose the effect of cooling on the reaction. And here's an example. We've got our anhydrous copper sulfate plus water makes hydrated copper sulfate. I'm just going to edit this slide because it just says anhydrous copper and that's not correct. Anhydrous copper sulfate plus water makes our hydrated copper sulfate. That reaction, the forward reaction going in the direction of this arrow, is exothermic, that gives out heat. The other way around is an endothermic reaction. When we heat our hydrated copper sulfate, we make our anhydrous copper sulfate plus water. That's endothermic. Now, if we add heat to it, the equilibrium moves in this direction towards the left, moves in the endothermic direction. So we end up making, at equilibrium, a greater amount of copper sulfate and water, anhydrous copper sulfate and water, but less of the hydrated copper sulfate. The reason being, the reaction's absorbing the heat we're trying to put into it, and the only way it can do that is by moving the equilibrium in this direction to the left. On the opposite side, if we start to remove heat from the reaction, we start to cool it down, the reaction is going to move in the right hand side and we're going to start to make some more of the hydrated copper sulfate. We start cooling it, the reaction is going to start to go more in this direction. This means we end up with less anhydrous copper sulfate on this side, less water, but more hydrated copper sulfate. And that's because the reaction is is releasing heat to counter the cooling that we are trying to do to it. So here again, the reaction is being stubborn. In summary, a closed system is one where nothing can escape or enter. Dynamic equilibrium occurs only in a closed system. Dynamic equilibrium means the rate of the forward and reverse reactions are the same, and so therefore the amount of product and reactants do not change at equilibrium, they stay the same. Le Chatelier's principle tells us that a change in the conditions of a reversible reaction will be opposed by the system. And the conditions are temperature, pressure and concentration. Alright, hope this was useful. It's a nice little quick one. Please leave any comments below. Please remember to like, subscribe and to share. If you've got any questions, please do ask them. Don't just sit there thinking I don't know what's going on. I think I've misunderstood this. I'm not getting this at all. Please ask the questions. There's no such thing as a stupid question for the chemistry. The stupid thing to do is to not understand it and not try and correct that. So there's lots of different ways of explaining this. This way it might confuse you a little bit, and looking at a different way of going through might work for you. So please do ask those questions. Okay guys, take care, stay safe and keep studying chemistry.